my budding chemists. I'm so glad to have you here with me, especially if you are interested in learning more about or reviewing titration. And I also wanted to very quickly, because I keep getting questions about my pens. I love these pens. I am not sponsored by this fountain pen company, but I just love them so much. And I will say, Twisby, if you do want to sponsor me, that'd be great. But in any case, they're called Twisby, and the way that it is written is TW. You can see it right here. Well, it's better if I just write it. TWSBI. So that's the company that makes these amazing pens. And the model, I guess you'd call it, that I get is Eco. All of these are the Twisby Ecos. And they have different tips on them, and they're so much fun to write with. So if you feel like going more old school with your writing, I highly recommend these. But I will warn you, they're not cheap. So if you need to buy a pen that's only, $1 or $2, these are not in that range. So, but they are refillable, which is why I love them so much. Okay, anyway, that was for all of you who have asked me about my pens. So I'll put them back. And then we will move on to those of you who have asked me to talk about titration. Okay. So what is a titration? Why do we do it? And this was a surprise to me when I was an undergraduate student in college. I was majoring in chemistry at the time. And I thought titrations were always, you are titrating one solution into another solution to determine the concentration of the unknown solution that you're titrating into. But it turns out it's really all about moles. It's all about the number of moles that are in the solution you're titrating into. So if that idea is a little bit confusing right now and you're wondering, why is she saying that? Let's talk a little bit about titrations by going through an example. Okay. So there are actually many different types of titration. It's not always acid-base. You can have redox titrations, for example, where you're carrying out a reduction-oxidation reaction with your titrant. Okay, there's also many other types, but by far, it is the acid-base chemistry that we look into the most often. Okay, and so what we're usually looking at is that the number of moles, if we're, sorry about the dog barking, that's my neighbor's dog, sorry. Okay. So if we're looking at a standard acid-base titration, which is what we're going to focus on in this video, this is true, okay, at the end point of our titration, okay? So, if you call it equivalence point, okay, these moles are equal to each other. So it's all about the neutralization. Where the net ionic equation, which we have talked about before, but put it is very common, and that is using an indicator. And that is a dye. And what's interesting about indicators, you could call it an indicator dye, or say it's a dye. These dyes will change color based on the pH. So it makes sense that you could also use a pH meter. And our students where I work, Willamette University, they do different experiments where they get experience doing it with the dye and also with the pH meter. Okay. So this example here of the net ionic equation, this is if you have a strong acid and a strong base. You'll end up with water, and your pH will be around 7. Okay, but if you're combining a weak acid with a strong base, or you could have a weak base with a strong acid, then your ending pH will actually be a little bit different than 7. So you need to know the system that you're working with in order to appropriately select the indicator dye that you want, or to understand what is the pH that you're looking for. And it's actually really fun to follow the pH as you are titrating, and you can see how the pH changes as you put in your titrant. Okay. So I've used that word titrant a couple times, and so why don't I just draw an example here of when you are carrying out the titration. Very typically, we have a burette, and there's a stopcock where you can control the amount of the titrant that is going in. Okay, and these are graduated so that you can get fairly precise measurements. Okay, so burette, that is the glassware that you use. And then I use a different color here, just so we can see a little bit better. Okay, doesn't necessarily mean that the titrant is colored. In fact, usually it's not. So, oh my gosh, this is totally bleeding. Look at this. Wow. Okay, I think I'm gonna not use this pen anymore today until I get this figured out. Okay, but this is the solution that's in here. Okay, and then this is what you're dripping down. I love this. It looks like blood. Oh my gosh. Wow, look at this. This is... Okay. I'm gonna actually find something to absorb this ink. Okay. So we're going real time. See how I work so hard for you here on this YouTube channel. Okay. So typically what we have here is the titrant is something where we know the concentration is known. Okay, and what you are titrating into, this is typically the unknown. Okay, also in terms of typically, we usually titrate into a flask. Okay, not always. There are reasons to use a beaker instead, sometimes we use a flask when we are using an indicator so that we can swirl it around. We can hold this with our hands and swirl and not have it splash over the edge. Now, if you are using a pH meter, then you might want a beaker because then there's room to titrate in and also room to put in the pH meter. And then usually you have a stir bar at the bottom to stir for you so you don't have to swirl. Okay. So different ways of doing this. Okay. All right. Now what's in here then? Okay. In here we have the unknown number of moles. Now this could also be unknown concentration. But either one is fine, okay? And why is that? This relationship, moles equals concentration, I use capital C for concentration, times V, volume. Okay? So this is concentration in moles per liter. So this would be volume in liters. So that way our units work out perfectly. We have concentration, I'll put this here, moles equals concentration, moles per liter times liters. So we can see how liters cancel out, give us moles. So here in our flask, you can either put in a solid, or perhaps you've weighed it out, all right, and you're trying to figure out how many moles. Perhaps you don't know the molecular weight, okay, or it could be unknown concentration, but you absolutely need to know the volume of it so that you can ultimately determine the number of moles based on the volume of the titrate that goes in. The concentration is known, and so if you know the volume and you know the concentration, you can know the moles. And if you know the moles of the titrant, and if it is either the acid or the base, then you know at the end point, moles equals the moles of the other one, the acid or the base, and ultimately you can answer your question. How many moles are there? What the concentration is, or whatever your question is. Okay. So let's consider an example where we can see this. And I hope I have my calculator nearby. Yes, I do. Oh, good. I hope it's working. Yes. And today, my calculator does funky things, but today it was quiet. It was just off and wasn't doing anything silly like it can do. Okay, so let us consider if we have HCl, and let's say, okay, this is our acid, and it has an unknown concentration. So that's our goal, is we want to determine what is we measure out, let's say, 15.00 milliliters. Okay, and then we put in the flask, our Erlenmeyer flask that I drew. Okay. And then, let's say we add indicator. A typical indicator for a strong acid-base titration would be phenolphthalein, which goes from colorless to fuchsia, a bright pink color, right around pH 8. So when it's a very, very pale pink, you can feel confident that it is right before pH 8, which is pH 7. Okay, so you can get some pretty good precision if you do your titration that way. Okay, we add our indicator, and then we titrate a strong base. So why don't we use KOH? Here's our strong base. Okay, by the way, this HCl, hydrochloric acid, this is a strong acid, so I'll just add that in there. Which has a known concentration so let's say the concentration is 0.023 molar. Okay. So that is not very many significant figures, so we know that ultimately we will only be able to have 2 significant figures in our final answer. Okay. If this were known to more significant figures, that would be great, but in this problem we only have the 2. Okay. So now we are going to titrate until we see pale pink. Now, note that if you use another indicator, not phenolphthalein, the color change will be different. Okay, there's, oh gosh, there's so many. Methylene blue, bromethymol blue, lots of different indicators. And some of them go from blue to yellow or pink to purple. Is there that one? Anyway, so when I say we see pale pink, that's because we are using phenolphthalein. Okay. All right. What was the volume? Okay, the volume of the KOH titrated until when we saw the pale pink was, okay, this is where we're making our measurements, and the final total volume that was titrated in was 23.05 milliliters. Okay. So what does this mean? Okay. What's our next step? Well, we go back to this idea here that if we are doing a strong acid-base titration at the endpoint where we have now neutralized the acid, we know that the moles of hydrogen ion equal the moles of hydroxide ion. Okay. And in this case, we have an acid that has one hydrogen ion and a base with one hydroxide. So we want to consider what is the chemical reaction that's actually happening. Okay, that is important because this is a stoichiometry problem that we're looking at. Okay. Stoichiometry is all about moles, and so is titration. It's all about moles. Okay? So, in this titration, what's happening is we have HCl. It's aqueous solution, and it is reacting with potassium hydroxide, so aqueous, forming water and KCl, the salt. The salt has the spectator ions. Okay. The net reaction, as I mentioned before, is hydrogen ions combining with hydroxide ions to form water molecule. Okay. So what we have here is a 1-to-1 ratio of hydrogen to hydroxide. And we do know the moles of hydroxide can be determined by multiplying the concentration times the volume. Okay, what's our concentration? Well, we were given that 0.023 molar, which is moles per liter. So I like to write this out as moles per liter. 0.023 moles per liter. And we'll multiply that by the volume. Volume needs to be in liters. Okay? We were given this volume in milliliters. So let's do a conversion. There are 1,000 milliliters in a liter. Okay? So this volume that was used is 0.02305 liters. Okay, so this is our volume. Put this here. 0.02305 liters. Okay, so now we get to multiply these two together. 0.023 times. Did I actually? Oh, that's so funny. 2323. Times 0.02305. It must be a 2-3 kind of day. Okay, what do we have? 5.3 times 10 to the minus 4. Okay, remember our rules of significant figures. We can only have as many as the number that has the most, the least number of significant figures, which we are confined by the 2. Okay. So this is, maybe I'll write it out, decimal point, 0.0053 moles. Okay, and again, this is moles of hydroxide. And guess what? Because we're at the end point, and because we have a 1-to-1 ratio in our HCl and our potassium hydroxide 1:1 stoichiometry. That means that we have this many moles by 3 moles of H plus. Or in other words, HCl, since there is 1 H plus per HCl. Now, if you had a diprotic acid, like sulfuric acid, for example, then you would need to take that into account here. Okay, so keep that in mind. Alright, so now what? Let's think about what we're trying to figure out. We are trying to figure out the concentration of the HCl. So we'll go back to the question, what do we want to know? We want to know concentration, moles per liter. Okay, well, we have figured out how many moles there are. Okay, so concentration of HCl, if it is in moles per liter, we now know how many moles? 3 moles. Okay. How many liters? Well, that's how many were measured out in this example. So with 15 milliliters. So we can convert this to liters. And when we do that, we would get 0.01500 liters. These are significant figures, but again, we're going to be limited right here by these two. So, but here's our number of liters. 0.1500 liters. And we are almost done. Okay, look. We will put in this 0.00053 divided by 0.015 liters. 0.035. And what are the units? Moles per liter. Or we can write it in molarity. 0.035 molar. This is the concentration of the HCl solution that was in the flask where we had put in 15 milliliters of it. We didn't know the concentration, but we titrated in a strong base where we did know the concentration. We measured how much of this base it took to reach the end point. This is how much we measured. Alright. And that allowed us to then carry out these calculations and determine the concentration of the HCl and get our final answer. Yay. Okay. Well, thank you so much for being here with me going through this titration problem. I will continue to take requests that you have and continue to make these videos for you to learn chemistry in a calm, slow environment. Alright, So I really appreciate you. If this is helpful for you, please subscribe, please like, and please share with anyone else you think could benefit from learning chemistry in this way. I love doing this for you, and thank you so much. And I'll see you next time.